Phase change. Heat capacity is used to determine heat transfer for a change in temperature, but another important category is heat transfer during change of phase. The phase of a substance can be solid, liquid, or gas. A gas is also called vapor. Phase depends on how the molecules are bonded. In a solid, molecules have fixed bonds, although there is some flexibility in their exact positions. A solid maintains its shape almost exactly if rigid and at least approximately if elastic, which means that the bonds can be stretched or compressed, but then the molecules return to their original positions. If the solid is plastic, bonds can be stretched or compressed and stay that way, so the shape of the solid gets distorted. A solid is almost incompressible because the molecules are next to each other. In a liquid, molecules are weakly bonded together, not fixed in their positions. Molecules can slide past each other, and a liquid does not maintain its shape even approximately, but rather flows to take the shape of its container at the surface below and may be flat at the surface above. Like a solid, a liquid is almost incompressible because the molecules are next to each other. In a gas or vapor, the molecules are not bonded and fly about freely, although there may be weak attraction at a distance between molecules. The molecules interact with each other and with the walls of their container by collisions. A gas is compressible, so it can expand and be compressed because there is a lot of space between molecules, and it takes the shape of its container. Both a liquid and a gas are fluids because they can flow, unlike a solid. One phase can change into another phase by a phase transformation. This can occur between every phase and in both directions. Phase can change from solid to liquid by melting, from liquid to solid by freezing, from liquid to vapor by vaporization, from vapor to liquid by condensation, from solid to vapor by sublimation, and from vapor to solid by deposition. During a phase change, matter maintains a constant temperature. This is fundamentally different from temperature change in a fixed phase. At atmospheric pressure, water boils and vaporizes at 100 degrees centigrade, and ice melts at 0 degrees centigrade. When ice melts and becomes water, the system of ice and water stays at 0 degrees centigrade until all the ice has melted. Just as heating and cooling are determined by heat capacity, heat transfer during phase change is determined by latent heat, capital L, which is the quantity of heat required for a phase change of 1 kilogram of a substance. So the heat needed for the phase change of a mass m of a substance is Q equals mL. Each transformation between two phases has its own latent heat, which is the same for both directions of transformation. Latent heat of fusion, LF, is the latent heat for freezing and for melting. We may drop the word latent and just call it heat of fusion. During melting of a solid of mass m, heat Q equals mLF must be added to melt it completely into liquid. The energy of the heat breaks the strong bonds between molecules, but allows weak bonds so that the solid becomes a liquid. During freezing, the reverse occurs. Energy is released as heat as strong bonds form between molecules and the liquid becomes solid. In this case, negative heat Q equals mLF is added to the liquid, which means that positive heat is lost. When a liquid of mass m vaporizes, positive heat Q equals mLV is added to vaporize it completely, where LV is latent heat of vaporization. This energy breaks the weak bonds between molecules and frees the particles to fly around apart from each other. In the reverse direction, vapor condenses to form liquid and releases positive heat Q equals mLV as weak liquid bonds are formed. In this case, negative Q is added to the vapor to remove energy. The third type of transformation is between solid and vapor, governed by Ls, heat of sublimation. An example of sublimation is dry ice, which is solid carbon dioxide, becoming vapor directly without melting first. In this case, Q equals mLs is absorbed biomass m of a solid. The reverse process is deposition, in which vapor becomes solid and heat is released. There can be huge differences between different latent heats and specific heat. Water, for example, has LF, heat of fusion, equal to 334 kilojoules per kilogram, and LV, heat of vaporization, equal to 2,256 kilojoules per kilogram. So it takes almost 7 times more heat energy to vaporize 1 kilogram, which is 1 liter, of water, than it does to melt 1 kilogram of ice. Compare these numbers with the 419 kilojoules it takes to raise a liter of water from the ice point at 0 degrees centigrade to the boiling point at 100 degrees centigrade. It is the very high latent heat of vaporization that makes a steam burn, or scalding, so bad. When steam condenses on skin, a lot of energy is released into the skin, which can cause a very bad burn. Note that freezing and boiling points depend on atmospheric pressure. When water boils, it forms bubbles because its vapor pressure becomes equal to atmospheric pressure. The water vapor then has enough pressure to push air out of the way and form bubbles. At lower atmospheric pressure, for example on a high mountain, water boils at a temperature below 100 degrees centigrade. Now let's look at an example that combines latent heat with specific heat capacity. The question is, how much heat is needed to raise 1 kilogram of ice that starts at minus 20 degrees centigrade to steam at 120 degrees centigrade? All of this is assumed to be at atmospheric pressure. First, we need to raise the temperature of the ice from minus 20 degrees centigrade to 0 degrees centigrade. The amount of heat, which we call Q1, is equal to the mass, which is 1 kilogram, times the specific heat capacity of ice times the change in temperature. And we know that the specific heat capacity of ice is 2.10 kilojoules per kilogram per Kelvin, and we multiply it by the temperature difference of 20 degrees to obtain 42 kilojoules. Then we need to melt the ice, and this takes place at a constant temperature of 0 degrees centigrade. We call the amount of heat Q2, which is just m times LF, and that is 334 kilojoules. Then we need to raise the water from 0 degrees centigrade to 100 degrees centigrade, and we've already seen that that is 419 kilojoules. We call that Q3, which is equal to the mass, 1 kilogram, times the specific heat of water, times the temperature change of 100 degrees centigrade. Then we need to boil the water, and this takes place at a constant temperature of 100 degrees centigrade, which we call the boiling point temperature. There's 1 kilogram of water, and we need 2,256 kilojoules to boil all that water into steam. The steam is now at 100 degrees centigrade, and its temperature must be raised to 120 degrees centigrade. The last quantity of heat we call Q5, which is the mass times the specific heat of steam times the temperature difference. So that's 2.00 kilojoules per kilogram per Kelvin times 20 degrees centigrade, and the mass is 1, and that is 40 kilojoules. The total amount of heat we need for the entire process is the sum of the heats from Q1 to Q5, which we find to be 3,091 kilojoules.